Helicopter Flying Handbook 7.1 Helicopter Performance. Let's venture into the realm of helicopter performance, a domain where a pilot's ability to anticipate and understand a helicopter's capabilities is of utmost significance. This understanding not only guides takeoff and landing decisions but also determines the helicopter's performance in various scenarios. Join me as we explore the key factors affecting helicopter performance and how pilots navigate the intricacies of this dynamic world. Helicopter performance hinges on a delicate interplay between engine power and rotor lift, be it from the main rotor or the tail rotor. Three major factors exert their influence: density, altitude, weight, and wind. The density altitude, a combination of pressure, altitude, and temperature, plays a pivotal role. While humidity is usually not a primary consideration, it does contribute to a 3 to 4% reduction in performance, especially in high humidity conditions. In the delicate ballet of helicopter flight, every percentage point matters. Weight is a variable under a pilot's control, making it one of the most critical factors. Adjusting the weight can be a pilot's key to conquering previously inaccessible locations. Higher gross weights demand more power for hovering, leading to increased torque and potential challenges during high-altitude operations. Wind, both in direction and velocity, introduces its own choreography to helicopter performance. Headwinds are favorable, enhancing performance, while crosswinds and tailwinds may necessitate additional tail rotor thrust for directional control. Exceeding the recommended wind limits could compromise tail rotor effectiveness, a risk no pilot should take lightly. Now, let's turn our attention to performance charts, invaluable tools in a pilot's repertoire. These charts are developed by aircraft manufacturers under specific assumptions about the helicopter's condition and the pilot's capabilities. The charts serve as guides, offering insights into takeoff, climb, and hover capabilities under various conditions. The height, velocity, HV, diagram, a visual representation of altitude and airspeed combinations, is a particularly powerful tool. By steering clear of shaded areas on this diagram, a pilot ensures successful autorotation landings after an engine failure, a critical maneuver in emergency situations. The HV diagram serves as a map of safety, cautioning against flight profiles that might compromise the ability to complete autorotative descents successfully. The shaded areas signify zones where a pilot might lack sufficient time or altitude for a controlled descent. Understanding this diagram is like deciphering a dance of safety, where the wrong step could lead to unfavorable consequences. As we conclude our exploration of helicopter performance, let's delve into the profound impact of weight versus density altitude on critical aspects such as autorotation, hovering, and climb performance. The height, velocity, HV, diagram, a guiding beacon for successful autorotations, operates within the parameters set by the gross weight versus density altitude chart. This chart, a regulatory necessity, establishes safer operational limits, cautioning against venturing into unknown territories beyond recommended gross weights. Pilots must recognize that operating at gross weights exceeding chart recommendations poses unknown risks, emphasizing the importance of adherence to these guidelines. Autorotational performance, a pivotal aspect of emergency maneuvering, relies on the interplay of indicated airspeed, IAS, density, altitude, and gross weight. While autorotational descent performance is primarily indicated by IAS, the final flare and touchdown phase, crucial for success, are significantly impacted by density, altitude, and gross weight. Increased density altitudes and heavier gross weights demand higher collective pitch angles, vital for overcoming the downward momentum during autorotation. The energy exchange during autorotation, powered by gravity, emphasizes the importance of maintaining target airspeed. The height, velocity diagram serves as a visual aid, cautioning against excessive airspeeds that could compromise the effectiveness of collective pitch application during the flare. Training autorotations typically focus on airspeeds between the minimum rate of descent and maximum range airspeed, emphasizing the critical role of maintaining optimal airspeed. Hovering, the pinnacle of power demand, dictates the feasibility of takeoff. Hover charts, accounting for in-ground effect, IGE, and out-of-ground effect, OGE, scenarios, consider variables such as gross weight, altitude, temperature, and power. As density altitude rises, the power required to hover increases, eventually reaching a point where power available equals power required, establishing the hovering ceiling. Adjusting gross weight influences the hover ceiling, with heavier gross weights resulting in lower ceilings. Climb performance, influenced by factors affecting hover and takeoff, introduces the crucial concepts of rate of climb and angle of climb. Best rate of climb speed, VY, maximizes altitude gain over time, while the best angle of climb speed, Vx, depends on available power. Wind direction and speed affect only ground speed, not climb rate, highlighting the importance of understanding these nuances in climb planning. In this intricate interplay of performance factors, pilots must grasp the delicate balance between weight and density altitude, constantly adapting to varying conditions. The chapter has equipped us with insights into the intricate calculations and considerations, providing a comprehensive understanding of the factors influencing helicopter performance. As we wrap up this chapter, remember, a pilot's decision-making is the choreography that ensures a safe and efficient performance in the skies.